All right. Hello, everyone, and thank you for joining us today for this week's session of the Parks College weekly webinar series. My name is Amy, and I'm the Outreach Coordinator here at Parks College. I'll be joined today virtually by Dr. Ebel and current engineering student Caitlin, who will be taking us around the electrical engineering program. We are very excited to have you joining us today from wherever you might be. Thank you for taking the time to virtually visit and learn more about the aviation and engineering programs at St. Louis University. In total, Parks College has programs available in aerospace, biomedical, civil, computer, electrical, and mechanical engineering, as well as flight science and aviation management and physics. So we hope that today something piques your interest. Before we start, I wanted to give you an idea of how this webinar will flow. In just a moment, I'll introduce Dr. Ebel, who will begin with an overview of the electrical engineering program and some of the activities that their students do. He'll then introduce Caitlin to share her perspective, and during the last few minutes, we'll open it up for some question and answer time. Throughout this webinar, we do encourage you to submit any questions you may have to the Q&A feature at the bottom of your screen if you're viewing through Zoom, or in the comment section if you're viewing through Facebook Live, and we'll do our best to answer as many of those questions during the last few minutes of our session. Throughout this webinar, you don't need to worry about turning off your microphone or camera. You can hear and see our presenters throughout the webinar, but we cannot hear or see you. This session will be recorded and posted to our YouTube page in the next few days, and you'll receive an email with that link when it becomes available. If you would like to view any of our previous webinars, you'll find those recordings in either a fall 2020 playlist or a spring 2021 playlist on our YouTube page. So now with that information out of the way, I am very happy to introduce SLU's electrical engineering program. And Dr. Ebel, I will let you take it from here.
All right, thank you, Amy. So the electrical and computer engineering programs, there's two programs here, are very typical for the types of programs you'll find in engineering colleges. Mathematics forms the foundation of the bulk of what we do. We go through the calculus sequence, differential equations, linear algebra, those sorts of things. And then we go, and then together with that, and also after that, we have students going through a variety of courses in this electrical engineering specialty area and the computer engineering specialty area to kind of learn a little, to learn about those ideas. One thing I want to do is I just want to go through and talk about some of the things that our students do very early in our program and throughout our program. So on the so first of all, students take an introductory course at the first semester freshman year and second semester freshman year. And in the first semester freshman year, we go through a variety of things. And what you're seeing on the right of your screen here is a website that I teach this particular course. And these are sort of the activities that we do. So one thing that we do, for example, is we put together a lemon battery. And the lemon battery is, I'm going to just pause that, and I want to get towards the end of the video here. This is a video that kind of talks about what this activity is, but literally with two nails that are of different metal structures and some leads to a volt source, you can create a battery. And the acid of the lemon is what creates the, or is what is one component of that battery. We have students putting together a paperclip motor. We have students putting together a 1-bit adder, which is the foundation of how algebraic arithmetic works in a calculator or in a computer. We have them putting together a speaker, just using paper plates, some paper, some magnet wire, and magnets and things like that. You can put together a paper plate speaker. And just to give you an idea of what this looks like, here is the construction, the instructions of it. And when you're done with an amplifier board and an MP3 player and the speaker that you've constructed with the cone, you can literally hear the sound that comes out of your speaker that's coming from the MP3 player. In the freshman year, we also do get into robotics. So we talk a little bit about ranging sensors, and there is a I'm going to pause that and kind of scroll down. This is what a typical ranging sensor looks like. So it sends out an acoustic signal which bounces off of an object and comes back. And we connect this to an Arduino, and the Arduino will provide a pulse signal to this ranging sensor that will send out a chirp signal. It'll bounce off of an object and come back. And the time of flight is what tells you how far away that object is. So through this, by integrating this, we need to find a conversion factor that can convert from time of flight in units of milliseconds, for example, to units of inches that the object is away. So there is a calibration procedure that is a part of this process. And there's a variety of issues that come into play. Here, this is an Atmega 328P. This is the processor board that we're using in this particular class. And this shows the sensor, and we can electrically connect those together, and we can make all this happen. We do program the processor board to actually perform to actually energize the sensor and acquire the time of flight coming back. We do the same thing with a DC motor. So there it, and these are videos. In any case, we talk about how to calibrate a motor and to be able to regulate the speed of that motor. So somewhere down here, I think I've passed it already. I show here we go. So this is an example of the Atmega 328P. We've got an LED board that we have the students manufacture in-house. And we've got this is just a power source and a DC motor. And we put a piece of tape on the motor, and then by spinning this and counting the number of revolutions per second for a given number, we can calibrate this motor so that we can drive it at any particular speed that we want. And so calibration is kind of an important part of what an engineer does to make things like motors and ranging sensors usable in an engineering context. So just to emphasize, this is what we do in the freshman year, and this is this is the first semester intro class, but this is a very hands-on class. This is a kind of thing there where the students are learning to do things that relate directly to electrical and computer engineering. This is our course from last spring, our second intro course, and you can see when the coronavirus hit. So sometime on September 16th, we were told that we were going to break, and then we were going to come back, and everything was going to be online. So I have some videos down here I can actually show, but we have students working with robots and calibrating those robots to be able to do something fairly simple like track a line. And tracking a line is actually not as easy as it may sound. So in this demonstration, you'll notice that up here on the left side, this is the Arduino code that we are writing. And there's two parameters here. There's a KP parameter and a KD parameter. And these parameters have to be set in order to get this mobile robot to be able to track this line. And I'm going to show a few of these. I'm going to show a few of these just to give you an idea of what this looks like at the start before you calibrate, and then what you can end up with when you're done calibrating. All right, let's get to where we actually do something here. Here we go. I'm downloading, and now we're running. And it's not tracking, and it's not tracking because the parameters are not set high enough. If we set the first parameter high enough, actually, I want to go back to right about here. Here is where we have started to control, but it's over controlling. All right. And then as you calibrate it, you can actually eliminate that oscillation and you can get it to track smoothly. All right, so that's what you can do if you use what's referred to as a PD controller to control it. And this is something our freshmen do. This is something that is very doable in the freshman year with just some basic knowledge introduced. And here I'm going to show a very extreme case where I'm going to put the robot at a very sharp angle relative to the line and watch that track. So our proportional control parameter is 332. Our differential is 665. So we had to calibrate that. So within just about 8 or so inches, that robot went from a very steep angle to tracking it extremely well. So those are just some of the things that we do at the freshman year that give you an idea of what our students do very early on. Here is another lab that we teach that involves a lot of practical projects that involve real types of systems that you might want to build. So for example, one project that we do is an echo cancellation project. And in the echo cancellation project, we inject echo into a signal and then we show how you can eliminate that echo. So where echoes can occur is on cellular signals. So you have a cell tower. Let me blow this up. You have a cell tower and you get a line of sight path from that cell tower to the cell phone that's in a car, for example. But that signal might also bounce off of the metal in a building and reflect and impinge on that same cell phone. So you actually have what we call multipath, which is nothing more than the signal along with an echo. And so this is actually a very practical type of lab where we talk about how you can eliminate the echo from a signal. And I want to show a very quick demo. So I hope you can hear this. What you're going to hear when I play this is you're going to hear the original audio. You're going to and then you're going to hear that same audio with an echo added, and then you're going to hear that audio with the echo removed. So I really like this lab experiment. So
Dr. Evil?
yes,
Hey, we did not hear the sound on our end.
you could not hear that.
No.
All right, let me try one thing here and see if I can make this work a little better.
Okay, thanks.
I'm wearing some headphones, which is probably affecting it. Tell me if you can hear it now.
The cow jumped over the moon. The cow jumped over the moon. The cow jumped over the moon.
Yeah, we heard that, and the second one with the echo. Yeah.
All right.
Thanks.
So so I laugh when I do this because I like to use nursery rhymes as our audio input for a variety of our experiments. My students get a kick out of that, but it's because we like to have fun with it. But in any case, that's an example where you can actually hear the result of eliminating the echo from that signal. And our students are designing the inverse filter to undo that echo from that particular signal. Other things that we do is we talk about AM modulation and DM modulation, and this is the same. If I can get this to come back. Let's try that one more time. All right, so we go through a discussion of how AM modulation works and demodulation. And this is the AM that you listen to in your car. if you're listening to, if your favorite sports is on a particular AM radio station, this is exactly how it works. So we go through the modulator. This is what's called the modulator, how you take an audio signal and convert it up in frequency to be able to be radiated out an antenna. And then we talk about the demodulator. Oh, and this shows what's called the RF spectrum, which is all the radio stations that exist simultaneously when they come into your antenna. So your antenna has to be able to split out one radio station, and then it has to be able to what we call demodulate it. So here is an example of what the demodulator looks like. It has a bandpass filter, a multiplier, a low pass filter, and a mean. We eliminate the mean from that, and that gives us back our baseband signal. And these graphs that you see here look kind of weird. These graphs are in a different domain. It's a mathematical domain that we call the frequency domain. And the frequency domain doesn't exist in the real world, but it is an important, useful tool that we use to look at signals in a different perspective. And I'm going to talk about this in a little bit with another lab experiment that we do. So another experiment that we do is we build a small speech recognition system to recognize the 5 long vowel sounds for the students across one group, A, E, I, O, and U. And what's interesting about this is that the human ear essentially hears in the frequency domain, not in the time domain. And what I mean by that is that when the signal comes into the ear, it goes, it impinges on the tympanic membrane, and it goes into an organ called the cochlea. And the cochlea is a sort of a spiral type organ that looks like this. And the and literally there's these membranes in between these two pipes, and these membranes are acquiring the acoustic signal in different frequencies. And the frequency domain is just that. It's taking a signal and breaking it up into individual frequencies. So just to show you that this is an example of an experiment that our students do, and they build a system to to recognize the 5 vowel sounds. And as a part of that, we take our audio signal, we pull it into the frequency domain, and then we go through a series of what are called metric spaces in order to separate out the vowels. So A is red, and E is black, and I is blue, O is green, and cyan is U. And we can actually go through at what's called a decision tree, and we can determine what was spoken. All right, there are other courses that we have. These fall under the realm of what we call special topic courses. So image processing is a special topics course, and image processing is kind of interesting because we go through some real world problems. So for example, one of the things that we do is we use what are referred to as morphological algorithms to solve real problems, like solving a maze. So we've all seen a maze like this apple down here, where you have to trace a path from the start, which I'm showing in the lower right corner, to the end, which is in the upper left-hand corner, and you can't go through any walls. But we use algorithms to do this automatically. So let me bring up some pictures here. So here are examples of mazes that have been solved using algorithms directly. This is a maze which is fairly complex, and that was done in less than about, I would say, 100 milliseconds. The algorithm was able to find that solution. Here's one that's much more complicated, and there's even one right here that I think is extremely complicated. And again, these all happen extremely quickly. So image processing can be used to solve a variety of problems. One thing that I want to emphasize is that with image processing, we do talk about how to use the webcam or a camera like a webcam as a tool for being able to determine real features in our field of view for use with a robotic system. So for example, here is an example of a picture where we have a natural coordinate system laid out on the floor with these tiles, because these floor tiles are 1 foot by 1 foot in size. So I have a coordinate system with the origin in the lower left corner, and we have some points in here. And by extracting the pixel values for these 4 points, we can map any point within this space into what you might think of as being floor coordinates. So you see this point right here that I have at x comma y, we can find that point in floor coordinates. Other things that you can do with these transformations is you can do what's called image blending. So you can take an image of a girl like this, you can break it up into sections. Each section has 4 corners. You can do the same thing with an image of a leopard. I think that's a leopard. In any case, and then you can merge each one of these corresponding sections together, and you can do image blending. So sometimes you'll see on your phone has the ability to be able to merge images together with some of these playful apps. Well, it's using a set of affine transforms to do that. And these are some of the algorithms that we talk about in our image processing course. The other thing that I want to talk about a little bit is junior design. And let me go back. I actually want to go back a couple of years because our current year is a little different because of COVID. But here is an example of let's go to, I think this is what I'm looking for. Yeah, this is what I'm looking for. So this is an example of a project that our students do in our junior design class. And the project changes every semester, so it's always different. But the idea is that on the floor, you have 4 red crosshairs, and those crosshairs form the vertices of a rectangular region. And then you have a robot within that region, and you have a webcam that's illuminating that's seeing that entire region. And using a feedback from the webcam, a processor on that robot can figure out where the robot is located. It can figure out its position and its orientation. And then using that, the idea was to travel from the start to the end. The start is in the lower right corner here, I suppose, as I'm showing it. And you have to navigate automatically from there to the end and miss or go around these obstacles, which were just pieces of paper placed on the space here, the play field, so to speak. And so they design these algorithms and go through this. I want to emphasize that our students function as an engineering design team in this course, meaning they go through all the same processes and procedures that a real engineering design team would go through, which means they have a critical design review, a preliminary design review, and a variety of things like that. I think I do want to say one more thing real quick before we end. We do teach a robot academy, which is virtual. It was virtual last summer. It will be virtual this summer. And I just want to show a little video that kind of shows what happens here. So this is a track that we provide the students. They put it together themselves. Here is an example of the robot. And this robot is going to do these little tongues sticking out of the track here are turn symbols. And the turn symbols are telling the robot whether to turn left or right when it reaches one of these junctions. And basically, you stay on the side that is smooth for these turn signals. So when it gets up to this turn signal, it's smooth on the right. So the robot's actually going to track right. This is smooth on the left. It's going to track left, and it's going to go around. This is going to say stay right, which means it's going to stay right here, and eventually it'll come to an end. But the students in 1 week put together this track. They put together the robot. They will program the robot to be able to detect these symbols and eventually end up at one of the stops. And these are the stops. In fact, I think this is where it'll stop right here. And you'll notice there are status lights on the top that tell us what the robot is doing and what it's detecting. All right, that's all I have. I think I'll stop sharing at this moment. And I would like to introduce Caitlin Zashki. Caitlin, would you like to? So Caitlin is a student who's in several of my classes this semester, as a matter of fact, and she has graciously volunteered to kind of give us her perspective on some things. Go ahead, Caitlin.
Hi everyone, I'm Caitlin Zashki and I'm a junior studying electrical engineering at SLU, and I'm actually originally from Springfield, Illinois. So if there's any questions about why I came to SLU or anything like that, I'm happy to answer.
Great, thank you, Caitlin. Dr. Ebel, thank you for your overview of the electrical engineering program. Again, at this time, if anybody has questions, feel free to put those in the Q&A feature or in the comments section through Facebook. We have just a couple minutes, so Dr. Ebel, I wanted to ask you a quick question, just
Sure.
from all of the content that you showed us. From sensors, batteries, radio signals. There's so much interdisciplinary content that goes on in the program. What do our graduates go on and do in their careers with that that variety of an education?
Engineering programs are very preliminary. They kind of get you in the door with a company, but when you get in that company, you'll spend about a year on a learning curve, learning the specific ideas and products that particular company produces. But the kinds of things that our students do, we have students that go to SpaceX and they work on rockets and things. We have students that will go to Ameren UE. They'll work on power systems. We have students going to Boeing. They work on airplanes. We have students going to places like Express Scripts, companies that you might not think of as needing electrical or computer engineers, but you'd be amazed at how many companies need electrical and computer engineers. It's quite a bit. Our placement rate is extremely high. It runs right at about 100% per year. So our students are very successful at getting jobs. I just talked to a student who graduated last May, who's putting together a manufacturing facility for a bottling company. So they're in Syracuse, New York, I believe, and they're involved in the design process and the construction of an actual facility. So those are just some examples of what our students do.
That sounds excellent. Very exciting. Caitlin, I'm going to turn it back to you. I heard you had an internship this past summer. Would you tell us about that and then also share your career goals as well?
Yes, of course. It was summer and the fall. I had a co-op with Ameren Transmission where I was in substation design, and that essentially is where you design substations. And I did a bunch of projects with like replacing circuit breakers and also like replacing relay equipment. And I got that internship because I had a previous internship actually with Legacy Audio in Springfield, Illinois, where I did a bunch of work with speakers and amplifiers, which was really interesting. But that kind of led me in the direction, was like, well, I kind of want to try something else. And so that led me to Ameren to work more in the power industry. And so after I graduate, that's kind of something I'm looking towards, is working in the power industry, because I also will have a internship with them this coming summer.
That is excellent. Thank you. And best of luck on that internship coming up. Final question for each of you. So Dr. Ebel, I'll have you go first and then Caitlin. What is one quick bit of advice you have for a high school student who might be looking at this engineering program?
I would say, first of all, I would say get involved in any project-based activities going on in your high school, especially if they're engineering related. If you have an opportunity to participate in the first robotics competition, that is a great way of getting some experience with a real engineering systems. I would also say, take some math, take physics and courses like that help to prepare you. I think that's also important. But as much as anything, just kind of stay aware of what's happening in the real world that's engineering related, and try to maintain some understanding of what really interests you. You know, when you get up on a Saturday morning, what are the kinds of things that you like to read about or look at or do?
Yeah, so my answer to that question would be definitely study, math and science if that's something you like to do and you want to get into electrical or computer engineering. But especially like maybe take a coding class if it's available at your high school. I know that was something that I didn't really have a lot of experience on when I came to SLU, but I mean, I was able to catch up quickly. But I would definitely think that would be something that's important.
Okay, great. Thank you both again, Dr. Ebel and Caitlin, for sharing your time with us and showing us
You're
the
welcome.
electrical and computer engineering programs. Again, a huge thank you to our viewers for joining us today. We hope that you did enjoy this virtual visit. And if you would like to learn more about the engineering programs at SLU, please visit slu.edu/parks. As always, please reach out to us at our email address, parksevents@slu.edu, if you'd like to connect further with our programs. For any teachers logged on today, we'd be happy to set up a virtual lab visit or guest speaker for your classroom this semester. Just send us an email to get that scheduled. And as Dr. Ebel mentioned, this summer we do have a virtual robotics summer academy that will be the last week of June into July. All high school age students are invited to register for that, where essentially we send you a robot kit. You log into Zoom each day with our faculty and our current students and with fellow campers, and you will build that little Arduino robot that was demonstrated earlier. And finally, please join us again in this space 2 weeks from now. And we're going to take a visit to the computer engineering program on Tuesday, March 30th at 4 p.m. So this concludes our webinar today. Thank you again for joining us. Happy St. Patrick's Day and have a great rest of your week. Bye-bye.